Hey everybody, so for today's lesson, let's just get started with this cylinder problem. You can use the formula that you were given during the video notes for this lesson for this section, 10.9. And what we're looking at here is a cylinder within a cylinder, so a thermal insulating sleeve. Think of it like a koozie for a hot water tank. It's just a gigantic one. Is going to help improve the efficiency. So the hot water tank is a cylinder. It's got a 13-inch radius and it's also got a 75-inch height, so over 6 feet tall. The sleeve is 3 inches thick, and you can see that that's labeled here on the top. And the insulating material that it makes up that sleeve is a fiberglass composite. So the question is, how many cubic inches of fiberglass composite are needed to create each sleeve? So cubic inches is a volume calculation. I'd like you to pause here and try it and come up with some kind of strategy. When we come back, I'll give you a hint to see if you are on the right track. Okay, so if you have tried this problem, then what I'm hoping for is that you noticed that the cylinder within the cylinder would actually just need to be subtracted away. So if you think about it as one outer cylinder and one inner cylinder, you will be able to, I just don't want to inadvertently reveal the answer here. So let me just get that out of the way real quick. Okay, so if you take the total cylinder and you subtract out the hollow one, both of them using the formula area of the base times the height, and on a cylinder the area of the base would be pi r squared. So if you do this calculation, total cylinder minus hollow cylinder, you should end up with your results. So you can pause again and go back and see where you stand on this. Okay, so for the total cylinder, we would be using radius 16 because from the center out to the edge would be 13 plus 3. So 16 inches would be your radius, and your height would be 75. And then if you did the hollow cylinder, you'd be looking at a radius of 13. And so you'd put that into the formula, and you'd still use height 75. You get those two, you subtract them, what you should end up with is approximately 20,499 cubic inches. So if we want to do that into cubic feet, we know that there's 12 inches in a foot, but if you think about it, we have three dimensions here, the two radii that we're using and the height. So we have to divide by 12 3 times in order to convert this into cubic feet. So you do that conversion factor 3 times and you end up with a total. All right, so moving on to the rest of this, just to do a quick recap of what you saw in your video notes. First off, you are working on a prism. And the prism is a three-dimensional figure, and it must have two parallel faces that are polygons. So circles don't count, that's what a cylinder will be. Must be polygons that are congruent to each other. The lateral faces that join them will go edge to edge, and they will make rectangles. So the length of the prism determines the length of the rectangle, and that actually is referred to as the height of the prism. When you connect the two parallel faces, that would be the height, even if it's laying down on its side like this. So we calculate the area of the face. We can use 1/2 times the apothem times the perimeter to do that. Or we can split it into triangles and calculate it that way. But whatever we do, we need the area of that base figure. And then we're going to multiply it by the height. And that'll give us the volume of our prism. With the cylinder, it's the same concept, except it's not a polygon at the end. It's a circle at the end. But if you get the area of the circle and you multiply that by the height, then you get your cylinder formula that way. You will call the lateral faces rectangles in a prism. In a circle, in a cylinder, it's a rectangle, the one that's cut and unwrapped, but you end up with a lateral surface area going around the side of the wrapper, so to speak, on the side of the cylinder. Okay, now the last thing that was covered in those notes is something called Cavaliere's principle, where if you take a figure and figure its volume, that same figure, when it becomes oblique, so if you tilt it, kind of like sliding a deck of cards off center, you will end up with the same area. So as long as the height stays the same and the cross-sectional areas stay the same, then it doesn't matter whether it's a right figure or whether it's off center. They will all have the same volume when that happens. So justification of prism volume is based off of layers. The base layer times however many layers there are, and that will be your height. And the same thing for a cylinder. This, if you want to read this, can be found on pages 39 and 40. And I encourage that you do because it will give you a better understanding of where these formulas come from. So 39 and 40 will give you those justifications. Think of the cylinder like stacking coins, and the number of coins would be the height. So you end up with a cross-sectional look that has those coins stacked on top of each other. All right, so for classwork, go to page 37 and work on pages 37 and 38, numbers 1 to 6. You can stop after number 6. Check your work on class kick. If there is time remaining, go to page 74 and do as many of those prism and cylinder problems as you can on pages 74 and 75. We should have notes for 10.10 ready to go for the next class period.